So, dear colleagues, dear friends, it is time to start the conference. My congratulations with the beginning of the conference. And we have mixed style. So some of people are here near the Black Sea. Some people are online. And we start with 2 online talks. The first talk will be done by Louis Kauffman. And the title presented here. So please.
Shall I start?
Please start, yes.
All right. This talk comes in 2 parts. I'm going to talk about the graph theoretic part first, and then we'll talk about related virtual knot theory. I'm going to be talking in a moment about the Penrose evaluation for finding the number of 3 colorings of a trivalent graph. Let's recall how this begins. This is pure graph theory, not topology yet. Recall the problem of 3 coloring the edges of a cubic graph or a trivalent graph. I mean that every vertex of the graph has 3 edges coming into it, every node. And we have 3 colors, where they could be 1, 2, 3, or A, B, and C. And at every node, we wish to have 3 colors appearing at that node. So here's an example of a graph that has been colored with 3 colors according to those rules. And the problem is to find out whether you can color your graph and how many colorings there are. In the case of planar graphs, this problem is equivalent to the famous 4-color theorem, 4-color problem. The way it's related to 4-coloring is by coloring the regions and then combining colors on the regions to obtain colors on the edges. So for example, in this example here on the right, I hope you can see my pointer. In this example on the right, I have colored the map with 4 colors using the colors W, A, B, and C, an extra color W. And then I combine the colors across an edge. So for example, white, color white will be the identity. And when I combine white and blue, I get blue. But if I were to combine A and C, then I get B. And in general, that's the rule, that if you take 2 colors and combine them, you get the third if they're both not white. And white is the identity color. In other words, I put a group structure on the set of colors, the Z2 cross Z2 plus C2. And by means of that translation, coloring the faces of the graph, coloring the map, is the same as coloring the edges with 3 colors. And the 4-color theorem then is the same as saying that a cubic 1-connected planar graph is edge 3 colorable. Well, we're not going to prove the 4-color theorem, but we are going to talk about ways to count the colorings. So if you have colored a cubic map, then you could choose one of the colors and mark those edges. And having done so, you'll see that you have a disjoint collection of edges that constitutes all of the vertices of the graph. That's called a perfect matching. By definition, a perfect matching is a collection of disjoint edges in the graph that encompass all of its nodes. And this perfect matching is even in the sense that all the cycles in the complement of the perfect matching edges have an even number of edges in them. That's because they're 2-colored. So you see that an even perfect matching is the same as finding a 3-coloring of the graph. And so the 4-color theorem, if you're thinking of reformulations of it, states that there exists an even perfect matching for cubic 1-connected planar graph. But the perfect matching is also of use for thinking about other things, as we'll see. Now, I want to also, for the sake of making certain kinds of arguments, reconfigure the coloring in terms of what I call a formation, terminology due to G. Spencer Brown. A formation is a collection of loops in 2 colors drawn in the plane so that given 2 different colored loops, blue and red here, they can share some part of their edge by either sharing in the form of one loop crossing the other, or in the form of one loop bouncing back along the same side of the other loop. You see that if you had a formation, then you get a graph, because a formation actually designates a collection of edges, some of which are colored red-blue, which we'll call purple, and some are colored red and some are colored blue. So if we take up here, A is red, B is blue, and C is purple, then I have drawn circuits on this coloring to obtain the formation. I draw along red, I continue drawing along C, I draw along red, I continue on C, I draw along red, I continue on C, and I come back, and that's one of the loops. That's a red loop. So another way of thinking about what is a coloring of a cubic graph is that it is a formation. It is a factorization of that graph into two colors of loops that interact in these ways. And this is useful for working out facts about the coloring. There's a question?
Yes, I have a little question just to have more concrete vision of the of the notion of formation. So, if you am I understand right that if you have your formation, then you can locally deformate do local deformation of the graph and put the additional edges, and then you can reconstruct some kind of a chord diagram. But this chord diagram, it's not exactly.
Excuse me, Alina.
Yes.
I'm not going to take any further questions from you. We should have a private conversation about different ways to formulate these things. If you please, no more questions during this talk, all right?
Okay. I'm sorry.
It takes too long.
Okay.
We'll have to talk privately about it.
Thank you.
All right. Now, as I was saying, you can locate directly the graph from the formation by walking along the formation along a given color. And when you get a double color, that's a new edge. And then you have a single color and so on. So you can locate the edges of the graph directly from the formation. There is no need to form extra constructions in order to go back and forth between formation and coloring. But it is important that you understand that a coloring can be rewritten in terms of interacting red and blue loops that cross one another or do not cross one another. Now, I'll come back to that, but here's the Penrose formula. This is found in a beautiful paper by Roger Penrose called On Applications of Negative Dimensional Tensors. And he says, you have a recursion formula, a skein relation. If you have an edge in the graph, then you will expand it, and you expand it by taking two vertices of the graph and removing one edge, and then connecting in such a way that you don't cross, minus the result of crossing. And I use a virtual crossing designation for the crossing here because it's useful to do that later on. And the value of a loop is 3. There are 3 ways to color a bare loop. So Penrose's theorem is that if you compute recursively in this way, using the skein relation, then the result will give you a number, and that number will be the number of 3 colorings of the graph. So let's look at an example, and then we're going to prove this theorem. Now, mind you, it's a planar graph. If you're not in the plane, if you don't have an embedded graph in the plane, this won't work, and we're going to fix it so that it will work more generally. But here's an example. This is a dumbbell and doesn't have any colorings, right? Because there's a loop at the end, and there's only one way to color that loop, and then there's an edge coming out. So there's no way to get 3 colors at either vertex in the dumbbell. When we expand it, we get a loop minus a crossover loop. And all loops, crossover loops or loops with no virtual crossings in them. They all receive 3, and so this is 3 minus 3, it's 0, as it should be because there is no coloring of this. On the other hand, here's a theta graph, and expanding it by taking parallel connection and crossover connection, I get 3 squared minus 3, 6. And indeed, this has 6 colorings because you have 3 choices for the leftmost edge. Having chosen one, you get 2 choices for the middle edge, and then only 1 choice for the remaining edge, making 6 colorings in all. As I remarked here, virtual crossings can be moved around. If you have, you can do Reidemeister 2 moves on them, and you can also move them across nodes. They're just indicating connections. And so you see in the intermediate expansion of the Penrose formula, you get some immersed curves, but you don't start with an immersed curve because it's a plane graph. You start with an embedded curve. So that's a very nice result. And if you were to believe Penrose's formula, you could perhaps use it as a tool to try to prove the four-color theorem, because another way of saying what the four-color theorem says is it says that a one-connected cubic plane graph will have a non-zero evaluation. Now, getting back to the formations again, I've drawn another picture of one. And you'll notice that in this case, this coloring, there's no crossings with this blue loop, but this blue loop crosses here, and then it crosses back, and then there's no crossing. So the number of crossings between a blue and a red is always even because these are Jordan curves in the plane, and the number of crossings between 2 Jordan curves is going to be even. That's the way in which I intend to use the fact that colorings are formations. Now here is a rather dense slide, which is explaining how Penrose defines his bracket and how he gets the skein relation from it. So what Penrose did was he associated to every node in the graph a tensor, a diagrammatic tensor, or as we say these days, he made a tensor network out of the graph. At a given node, you have indices I, J, and K, and the evaluation of that node, if you had indices put down, and the indices run from 1 to 3 because we're 3 coloring, is the square root of -1 times epsilon I, J, K, where epsilon I, J, K is the sign of the permutation 1 to I, J, K, or 0 if it's not a permutation. So epsilon 1, 1, 2 is 0. Epsilon 1, 2, 3 is 1, epsilon 1, 3, 2 is -1, and so on. So the permutation sign can be thought of as read from the going around clockwise in the diagram I, J, K. And if you saw a 1, 2, 3, then this would be a plus I. And if you saw a 1, 3, 2, it would be a minus I. So then Penrose labels tensors on the graph. Every node becomes a tensor. And then every index occurs twice in one tensor because every index occurs at the ends of its corresponding edge. And so you would get a tensor, in this case, you would get root -1 epsilon I, K, J, root -1 epsilon I, J, K, and you're supposed to sum over all repeated indices to contract the tensor. Summing over all repeated indices means that you label the graph with 1, 2, 3 in all possible ways. But the only ones that will survive are the colorings, because the epsilons are 0 whenever you don't have the local condition for the coloring. So this Penrose sum over the products that come from the evaluations of the tensors, it is a sum over all colorings, exactly the colorings. And what needs to be seen, among other things, is that every coloring receives +1 for its product of plus and minus square roots of -1. Once we see that, then we will get a count of all the colorings, and bracket G will indeed be the number of colorings. The other part of the Penrose formula is the identity which is in fact a tensor identity about the epsilon. So from Penrose's point of view, this identity of his, this Skene relation, is actually an identity about the epsilon, which I think I have better explained in the next slide, or maybe just indicated it a little bit. That is, if you think of this as epsilon ijk, and there's a k here, then this one would be epsilon something k something. And these might be I and j, and these might be I and j, or this might be I and j, and this would be j and I. So it depends on the order. If you have two indices here, the two indices down here will have to be the same, and you'll have a third index in the middle. So when they're the same, on the left-hand side, you can see that the permutations have opposite sign. The cyclic orders are opposite, and you get minus. And when they cross over, so that you had a label I here and a label I down there, in the crossover position, you'll see that you get the same thing. Try it out. 1, 2, 3, and 1, 2, 3. That's crossover. 1, 2, 3, 1, 2, 3, both plus. So the identity, the Skene identity, is actually an identity about the epsilon, and it's related to the vector cross product, but I will not go into that here. So we're left with the Skene identity works, and we want to see that the products of the i's, plus and minus, that occur in Penrose's tensor contraction is equal to 1 for each coloring. And in order to do that, I'll think formation, and then I can see the proof very easily. Here is what happens if you have blue crossing red. You have red, blue, purple, but then you have red, blue, purple. They're both the same. They're both plus root minus 1. Now, if you had done it in the left way, it could have been minus root minus 1, but the other one would have been minus root minus 1. The product of them is minus 1. Whenever there's a crossing, you get a minus 1. Whenever there's a non-crossing, you get something like this, red, blue, purple, but the other one is red, purple, blue. So you get an I and a minus I, and the product is 1. So now you see how the square root of minus 1 is working here. I times minus I, 1, that's when you don't count a crossing. And I times I, or minus I times minus I is minus 1. That's when you count a crossing, and every crossing is counted with a minus 1. But there are an even number of crossings. As we said, a typical example like this, you have an even number of crossings between blue loops and red loops. So therefore, you will have minus 1 to an even number, and that will be the contribution of the tensor for that coloring, and you're going to count every coloring with a plus 1, and you count the number of colorings. And that is a proof of Penrose's formula. So far, so good. But now we have the following. If we were to take a graph which is not in the plane, like this K33 here, this is a non-planar graph, and that crossing there, that virtual crossing, is necessary in order to draw it in the plane. There's no immersion of this graph in the plane that doesn't have some extra virtual crossings. We could then apply the Penrose formula to this picture, but when we do, we get 0. And you can see why we got 0 by just doing the expansion. I expand on this edge, and I expand on it parallel and crossover. And now this little crossover of the immersion has no effect, and it's the same as this box with 2 curves on the side. And on the other hand, when we put these 2 virtual crossings together, when we have the crossover, then this is the same as a box with extra edges on the top and the bottom. But these 2 graphs are isomorphic, and so further evaluation will give you the same result. You get 0. It gives you 0, but the number of 3 colorings of this graph is 12, as you can check. Certainly not 0. So the Penrose formula is giving the wrong answer in this case. and we want to fix it. But you can see, if you start to think about it, what should be the right way to fix it. Because when you color this, and I could have drawn an example, but I didn't, then this might be blue here, right? And this other edge going through that immersion crossing might be red. And this is a crossing between a blue and a red, and it's not being counted as a -1 or anything. It's just being ignored. But if that means that for this coloring, for the one where this is blue and that one's red, we would be getting perhaps -1 from the tensor rather than plus. We need to count -1 for every time blue crosses red. So that leads to the following notion, that for an immersion crossing, which I'm going, an initial immersion crossing that is from the embedding of the graph that I started with, I'm going to add a new tensor. And my new tensor is going to be 1, if the lines cross over one another with the same, with colors going straight through, but they're different colors, then it will be -1. And if they're the same color, it will be +1. And you see that if we put that in, that will compensate, that will make sure that in the Penrose sum, every time you hit a coloring, the tensor will give you -1 to the number of crossings of the blue curves with the red curves, and it will be even because you're counting all the crossings, and they are curves in the plane after all. So that's an answer to extending Penrose to give you a correct color count. And you can try it out. For example, here's the K33, and we expanded it into these two. But now it's a different story because this one over here on the right has a combination of a standard virtual crossing, which we don't put any tensor on, and the significant virtual crossing that came from the immersion. So we can't just cancel that out. We have to follow it up. This combination of one kind of virtual crossing and the other kind of virtual crossing for the immersion doesn't pull apart. So then we continue our expansion. The one on the left simplifies to this. The one on the right can be expanded on this edge in this way, and I continue my expansion. Now, I'm not going to go through it in detail, but you see that as I go along, certain parts get evaluated because we can count them, and other parts have to be kept track of because of the immersion crossing. And in the end, we get this special guy here. And this special guy will give us different results depending on whether these are colored the same or differently. So let's just stop and think. You have two loops. If they are colored the same, then we don't put any funny sign and we get 3, because if they're colored the same, there are 3 ways to do that. If they're colored differently, then we get to color one with 3 and the other with 2, and that's 3 times 2 is 6, gets a minus sign. So the evaluation of this is 3 minus 6, and that in the context of the rest of the calculation gives the 12 correctly. So this is the way I can extend the Penrose formula like this to get it to calculate the number of colorings of any cubic graph. You just take your cubic graph and push it into the plane, make an immersion out of it, and put a tensor for each immersion crossing that counts whether you get different colors going through it or the same color going through it, and then do the counting. So this is of use if you want to think about colorings of non-planar graphs and so on. So here we are. We're going to next generalize this further. We want to have some polynomials rather than just evaluations. And then we're going to see how it's related to virtual knot theory. So the first thing I'm going to do is the following. I'm going to generalize my Penrose evaluation to a polynomial. So that, and I'm going to do it in the simplest way from the point of view of the graph theory. We'll leave the Penrose-Skene relation alone, but we'll evaluate the loop as delta, an algebraic variable, rather than 3, and see what happens. Now, what does happen? I want to skip a slide and come back. Here we are. I hope you can see the entire picture. Part of it is a little obscured on my screen. Let me get that out of the way for myself. So now we're evaluating the loop as delta, and I'm going to choose a perfect matching to do my evaluation, because a perfect matching is exactly the way to make sure you can evaluate everything in a systematic way. You see, I'm going to expand on all the perfect matching edges, and that will give me an answer. So once I choose a perfect matching, I definitely have a well-defined polynomial, graph polynomial. If you expand on an edge near a little loop like this, a bubble, you see you get a loop minus the crossover, which gives you delta minus 1 times the result of not having it. So if this was ordinary 3 coloring, this would be 2, multiplying by 2. And in my generalized case, delta minus 1. So now I'm going to try evaluating a polynomial for this graph. So I expand it by my method. No worry about immersions here. I just go ahead and expand it. And I end up with 2 delta squared minus 2 delta. Now I do it with a different perfect matching over here. Oh, but I get a different polynomial. I get delta cubed minus 2 delta squared plus delta. That's what happens. If you take delta equal to 3, you'll get the same result, because Penrose doesn't matter how you expand it. And indeed, you see that 2 times 3 squared minus 2 times 3 is equal to 3 cubed minus 2, 3 squared plus 3, a little arithmetic. So what happens is that you can do this. You can do the graph theory of generalizing Penrose to polynomials, but in order to do that, you have to choose a perfect matching. And then the structure on which the polynomial is defined is a perfect matching of a graph. And different perfect matchings can give you different polynomials. So that means that there is no graph isomorphism carrying perfect matching edges to perfect matching edges between these 2 perfect matchings. You can distinguish perfect matchings with this polynomial. Well, we would like to do this. We would like to have this defined for immersions as well. Let me go backwards now. And so we can do that. We're going to have an immersion crossing. And how are we going to define the valuation of the immersion? Well, essentially the same way, but there is a good way to think about it, and that is this: that we evaluate the immersion crossing by saying that it's 2 times weld minus ordinary virtual crossing, which gets evaluated in the usual way. Weld means that these have to be colored the same. So this is like a deletion contraction formula in graph theory. This is contraction, must be colored the same, can be colored anything. And you can see that in the case when these are colored differently, then you will get the minus 1. And when they're colored the same, you will just get the usual virtual crossing. Not hard to see. It comes from anything is equal to same plus different. And this says that that what we wanted was same minus different, right? When they're the same plus, when they're different minus. But same minus different is twice same minus anything. And so that's twice same minus anything. It's a logical identity. And then we can evaluate. So for example, if we had a weld, this would be delta because they're the same. If we had this guy, which was this, then it's twice same minus whatever. And this is 2 delta, and this one is delta squared. So we get 2 delta minus delta squared for this one. So that's how we generalize this further to the immersion polynomial. And now I'm going to show you something that came up a little later for me. All of this was understood a while back, but then Scott Baldridge and Ben McCarty started working on something which I don't have time to tell you about, a homology theory that's related to the graph theory. And in their homology theory, they ended up using a color count on perfect matching graphs, and their color count is a natural generalization of the 3-color count. And it is something we could have thought of before, but it came up in their work. And then these evaluations turn out to be important for their work, and you'll find a paper on the archive by the 3 of us showing how this special evaluation here is related to the homology theory. It's related to the Euler characteristic of the homology theory, but we won't go into that. We're staying with the graph theory here. Now, how are we going to color? We're going to color in the following way. We've got n colors now, 35 colors, not just 3. But we insist that in a perfect matching graph, we're going to color. And we aren't worrying about coloring the perfect matching edges, just the ones that are not perfect matching edges. And 2 edges that come into a perfect matching edge will be colored differently. And at the other end of that edge, the same 2 colors have to occur. That's the color condition. Now, of course, that happens for the 3 coloring because you have, say, red and blue, and this is purple, and so you have to have red and blue over here. But here we have many colors, might have red and blue coming in here. You have to have red and blue here, but they can come out in either order, red, blue, or red, blue, blue, red. So that's the color condition that we're going to think about. And then we're going to see that this counts those colorings on a perfect matching graph. So when we generalize to have the loop value be some n, then it still is counting colorings. It's counting these perfect matching colorings. And we want to see why that is. So here is the basics of this. We have a tautological expansion for this kind of coloring. What did we say? We said that we're allowing A and B and then A and B in that order, or A and B and B and A in the other order. And I missed the perfect matching edge designator there. But the perfect matching edge then expands into same in the same order or same in the opposite order and different in both cases. So that's what these little glyphs mean. Different, but it could be different and crossing over or different. And now I'm just counting constructions of colorings. I'm not counting numbers. So the number of colorings of this is equal to those colorings of these 2 loops that are different, plus those colorings of a single loop that are different from itself. There aren't any of those. But the number of colorings of 2 loops that are different is n times n minus 1, and that's the number of colorings of this. Okay, that's just like before in this case. And you can compare this with the Penrose type expansion, which counts it correctly in a different way, right? 2 loops minus the single loop, but now we count n squared minus n. We get n times n minus 1 again. So the way you prove this is you generalize, or the way I prove this, and it comes out of the homology theory in a different way. The way I prove this is you define a new tensor, and the new tensor is defined with 4 legs for each perfect matching edge. And it is, of course, it's tautological. If I equals k and j equals l, then you have plus. And if I equals L and j equals k, you have minus. It's just like before, only there it is, and the circle is n, okay? And then the immersion crossing is 1 and minus 1, just as before, which is 2 times weld minus crossover. And we have the Penrose expansion. And then you have to think about this, but if you think about this carefully and think about how these colorings can also be written as formations in the same way we did before, then you see that the arguments that I already gave you immediately generalize and tell us that this counts those colorings. And it counts colorings in a generalization of a Lie homology theory in that homological picture of Baldridge and McCarty. So here's an example of doing this, and of course it works out. I'm not going to bother you with this example any further because we want to go on. But now that's a summary of how the graph theory works. And the graph theory can be explored further because there are very interesting graphs that don't have any three colorings. This is an example of an uncolorable three graph, uncolorable cubic graph, non-planar, related to the Peterson graph. And there are many things like this, snarks, things that won't color with three colors, but they get non-trivial perfect matching polynomials. And so they get higher order colorings, and there's a lot to explore here in the graph theory. Now here's where we're going. First of all, we could have made a more complex polynomial. I could have put arbitrary variables x and y for the smoothing and the crossover, and another variable delta. And we would keep the double virtual chromatic evaluation. We would keep all that, and we get a more general graph polynomial. But now if you start to think, this looks very analogous to the knot theory, and how do you make the analogy work? Well, one way to make the analogy work is to send a perfect matching edge over into a knot theoretic crossing coupled with a crossover. You'll see why I do the crossover instantly. Because you see, if I put in the crossover, then the crossover in this formula will have another crossover on it, and you'll get a smoothing of the usual kind. And you will find that over in the knot theory, the expansion of a crossing will be x times one smoothing plus y times the other, a bracket polynomial. And this is going to be a generalized bracket polynomial with this extra virtual crossing on it, because that's what we've been investigating today. So this suggests that we should be looking at a virtual knot theory with two types of virtual crossing, and to see what kind of generalization of the bracket is going on when we do that. So I'm going to skip to another slideshow to talk about that for the last part of this talk. Oops. Oh, sorry, I don't want that. I want the full screen. Okay. So here we are again. And now I'm talking about multiple virtual knots and links. And while there is a kind of functor which takes you from the graph category over to the knot category, I'm going to now dwell in the knot category. So I'm not talking about the properties of that functor either, which of course is interesting because it means that you can pull things from virtual knot theory back to graph theory and across. But we won't worry about that. We're just going to talk about what I'm going to call multiple virtual knot theory. Now, in the notation for this, I will use a standard virtual crossing, and then I'm going to have another one with a box. And I could have lots of them. Hello? Question? Okay. We can also label virtual. We're going to consider virtual knot theory with many virtual crossings. So here are two that I like to draw, but I could have many indexed by some index set if I want to. Now, we have thought about different variants of virtual knot theory before. For example, earlier we have thought about hierarchies of virtual crossings, where you might have virtual crossings of type 1, type 2, type 3, type 4, and higher orders can detour over lower orders, but not the other way around. That's interesting, but that's not what I'm going to do here. Here, it's a level playing field. We're going to have many virtual crossings, and they all detour over one another. And of course, they all detour over the classical crossing, and there's one type of classical crossing. So that's the sort of virtual knot theory I'm going to do. And with that, allowing detouring over everything in that way, the basic axiom for the theory is that that we will allow arbitrary detouring and we will allow classical Reidemeister moves. And that gives us a virtual knot theory. And you can look at some examples. So for example, here, I have a link. You see, these are two different virtual crossings. I haven't said that I could pull them apart. I can only do Reidemeister moves or detours on one crossing, but I don't get to detour them both out. I only use a detour for one. A detour means a consecutive sequence of virtual crossings of a given type. Then you can move it. You don't get to detour multiply. All right. In general, if you had one type and another type, you don't get to do a detour there. Just detours within each virtual crossing type. So that defines, in general, a virtual knot theory that is going to be of interest. So then you see, in that context, we can do a bracket expansion of this kind where there are going to be two virtual crossings in the theory I'm now considering. And one of them is quite different from the other in that it has this expansion, 2 times weld minus cross. And then all the rules for this are the ones that we discussed already. So I'm not going to actually go through these slides, but you can see that you can, if you work on it, see that everything works compatibly. And if we adjust the variables to A and A inverse and the usual value for the delta, then we can get bracket invariants in this virtual knot theory for these kinds of knots. So for example, over here, I have calculated over here, I've calculated this virtual trefoil, which has 2 virtual crossings and 1 real crossing, and I'm finding that it has a non-trivial result and that it's distinguished from its mirror image by this generalized bracket. And we are non-trivially using the immersion crossing and the way that it behaves differently from the other crossing in order to do this. Another example of this is the following. Here is a virtual knot with the same virtual crossing here, and that one has Jones polynomial equal to 1, bracket trivial. If you put the immersion crossing and the regular virtual crossing, then of course it's non-trivial, and you can calculate that from the new bracket polynomial. Other things generalize in a similar way, and they're going to be quite interesting to explore. For example, the arrow polynomial is an oriented, expanded version of the bracket where we keep track of these nodes, these cusps that occur in the disoriented smoothing. It turns out that for invariants, 2 cusps on the same side of a line cancel one another, but a zigzag cusp doesn't have to cancel, and you get lots of states that survive like this. But if we have more than one virtual crossing type, then there are many, many extra states. For example, there is this one here where these are kind of welded together by a pair of different kinds of virtual crossings, and they have zigzags in them. So there are many, many irreducible states that will contribute to an arrow polynomial generalization. Here I've given an example of calculating it and getting a particular kind of arrow reducted state when I expand it. So you see that there's a whole area of investigation that needs to go on. I can ask the question, is there a surface interpretation for multiple virtual knot theory? If you think of a virtual crossing as a handle detour, then you could have handles that are labeled by the different virtual crossing types and play with that. But I don't claim to have a good interpretation, one that I'm proud of. I can just think that way, and I'm still thinking about it. There's a paper in preparation here, which I haven't finished writing. In welded knot theory, you can also do the same thing. We can define multiple welded knot theory, where you would have forbidden moves that go across the welded cross, the new virtual crossings. Forbidden move over type, and that would be the natural generalization of welded knot theory. You could also have you could also decide to have what I call strong multiple welded knot theory, where you allow over forbidden and under forbidden moves because of the fact that you will still get some non-triviality due to the concurrence of different kinds of virtual crossings. And then finally, I want to mention an algebraic invariant that one can define here. If you in just general multiple virtual knot theory, here is a virtual crossing. And for each virtual crossing, I will choose a free element V alpha for a quandle that I'm going to define. And I'm going to have the usual quandle rules. Here I'm doing it, I'm going to have the usual quandle rules for an oriented quandle at the crossings. But then at the virtual crossings, I will have an action of the free element that corresponds to that virtual crossing. So B here will go to B star bar V alpha, and A here will go to A star V alpha, according to the orientations, which I didn't draw, or according to left and right. I haven't been careful about my orientation in this diagram. But then you can see that the resulting algebraic structure with these relations at the crossings is invariant under detour moves for each of the virtual crossings. That's because each detour corresponds to that virtual crossing type and not the others. And so we get a generalized algebraic structure for any given multiple virtual crossing theory of this kind that is worth investigating. You might be interested in seeing one small example of that, so we'll finish with that example. Here I have drawn the relations for this two virtual crossing trefoil knot. I've just drawn them out with the free elements, and I get a certain long relation here. And you can analyze the algebra of that in general if you want to. But you can also do a generalized Sawalik polynomial by using the Alexander quandle at the classical crossings and using just simply multiplication by a module element, a extra free module element for each of the virtual crossing types. So you'll multiply by V for one and W for another, and you can then get a polynomial. So that's something that you can actually calculate. So for example, here I'm doing the generalized Sawalik polynomial for my virtual trefoil here, and I have two elements. I have a W for this, and I have a V, and I work it out, and I get a non-trivial polynomial as a result involving V and W. If V were equal to W, that would be the case where these two virtuals were the same, it would pull out and be trivial. As you see, it will be 0. But with v not equal to w, that's reflecting that these two virtual crossings are different, and we get a non-trivial result for the invariant of this trefoil knot. So what I'm saying here is that many of the invariants of virtual knot theory do generalize in quite non-trivial ways to multiple virtual knot theory, where multiple virtual knot theory means for me here that you have as many virtual crossings as you like, and each virtual crossing has its own detour ability, and so they are all on a level playing field with regard to one another. But when they interact with one another, they don't necessarily cancel each other. And that, I believe, is quite an interesting formal generalization of virtual knot theory, that because of the graph theory that I started with, has some very non-trivial things to look at right at the beginning. And that's the project. There will be a paper about this in a couple of weeks, I hope. And I'll stop there.
And there were some questions in chat. Maybe we can start with questions in chat.
Let's see.
Please, can you show us a chat?
All right, I'm looking at the questions. What if we embedded the K33 on a Mobius band? That of course is a nice question. I haven't thought about what happens to. I have been thinking recently about invariants in RP3 and things like that. We can try doing some of this in non-orientable surfaces, yes, but I don't know the answer here. Is it related to enumerative questions about the number of quadrics and cortex? It might be. Vasily says, sometimes minor closed properties correspond to properties that are not minor closed. It seems that the existence of 4 colorings exactly corresponds to this property. An example of minor closure in relation to 4 coloring that is of interest to me is the famous Tutt conjecture. Tutt conjectured that if you have a graph which is not colorable, like the Peterson graph, then in fact it would have a Peterson minor.
I'm sorry, could you repeat the last sentence?
Yes, Tutt conjectured long ago that a trivalent graph, not necessarily planar, of course, that is uncolorable and one-connected, so it isn't.
For example, Penrose graph.
For example, the Peterson graph.
Peterson graph, yeah.
But Tutt conjectured that the Peterson graph is generic in the sense that any uncolorable has a Peterson minor.
What does it mean, Peterson
minor? Minor means that by deletion and contraction, you can get down to that graph.
But may I ask, is it related to very general? I mean, if Peterson graph corresponds corresponds to the graph of intersection of some very interesting and the space. I mean, some half of the dodecahedron, and it's related to the five-fold I mean, we have perturbation of 5 sheets, and in the different parts of our, I mean, all this set describes
Well, what are you saying? Peterson is related to a lot of structure. It's related to the way, by the time we got to S5, there are some very non-trivial permutations that can happen, and Peterson is constructed out of that. And there are many, many properties of the Peterson graph. There's a whole book about the Peterson graph. It ends up being related to examples in graph theory in many ways, right? And it is the simplest non-trivial graph that we know that's uncolorable. And Tut thinks that it's generic in the sense of minors. No one has disproved this. And it's partially proved in some cases. That's an example. There's more about minor closure, I'm sure. Vasily asked a good question here.
Does it mean that this is an existence of some part of, it's not an object, it's just we have concrete example of some things that could not be listed in the way of I mean, usually mathematicians use numbers. I don't like numbers, but if we don't want to count, we can.
I'm not sure what you're asking. If we say it in a qualitative way, then we're saying Tut's conjecture is that the way the Peterson manages to be uncolorable is really the only way that uncolorability happens in some sense.
So
I'm sorry. Since we go to the very deep particular discussion, are there other questions? So please.
Analogs of well, this is more about minor closure, and then Vasily had a lot of yeah. He says different crossings should be parity like yeah. There will be picture valued things. I'm saying that we're dealing with picture valued things, but then the whole idea of picture valued things will come in again in this generalized virtual theory. What if one recognizes in this picture of topology a real algebraic curve? Well, yeah, I don't know how it's related to real algebraic curves. That's a good question.
It's the common, okay, it reminds the Riemann-Hurwitz formula and Harnack and formula for Harnack curves. I mean, the number of the one of the examples when you counted the number of colorings, and it was the half of n and n minus 1 in terms of curves. It can be related to the sixth Gilbert problem, and it's I mean, real algebraic geometry have the similar
yeah, so we find ourselves doing certain kinds of counting with the graph theory. Such counting might well happen in another category and be related to it, like the category of real algebraic curves, quite possibly. Discrete counting happens in some specific category that you're working with, and it ends up being related to the combinatorics. Can happen very easily. We're going back and forth across that idea a lot lately, right? That we're thinking, well, what kind of discrete counting or geometry can we count out of a situation? And maybe we can use that to get topological information. That's a theme that goes on and on, right? This last question says,
thank you.
There's one last question here. Would corresponding theory of flat virtual be different from the usual one? Well, yeah, I'm showing you that it's certainly different, but it's highly related to it. It's quite, this theory of flat. Yeah, flat will definitely be different from the one that I was describing. We can do flat, but flat has its own properties. It will be different from the usual flat theory, for sure.
Okay, thank you very much. I'm sorry very much. We have very dense program and it's time for the next talk. So let us thank speaker again. Thank you very much. Very interesting talk.